In this video, we solve problems number 5 and 6 from the differential equations quiz number 6 from the spring 2021 semester. There were multiple forms of this quiz. These are the questions, excuse me, that appeared on version B of the quiz. These questions cover standard L26, which is about the shifting theorems, also known as translation theorems, the unit step function, and convolution. So in this standard, we're not actually solving any differential equations or integral equations or integral differential equations using the Laplace transformation, but we're practicing our techniques involving the shifting theorem, unit step function, and the convolution theorem. So this would involve transforms and inverse transforms of functions using all three of those. So in our first question, we're asked to consider the function f of t equals 2t on the interval from 0 to 4 and 5t minus 4 on the interval from 4 to infinity. And we're asked to use the definition of the Heaviside function and one of our shifting theorems to find the Laplace transform of f of t. And then I gave you this hint. I said, you may want to write f in terms of the Heaviside function first, and then apply one of our shifting theorems to find its Laplace transform. So that's what I'd start with. Remember, our Heaviside function is like an on-off switch. It's 0 until you get to a. The Heaviside function at t minus a is 0 until you get to a, and then it's 1 after that. So it's off, if you multiply any function by that Heaviside function, it turns the function off until you get to t equals a, and then at t equals a, it turns it on. With that in mind, the first thing that we'll do is we'll write f in terms of the Heaviside function. Or one of the infinitely many Heaviside functions. And we do this again by thinking of the Heaviside function as an on-off switch. So we always start by writing f as whatever it is initially when t equals 0. So we'll turn on the function 2t. And that's at t equals 0. We're doing that. And then at t equals 4, we want to turn this off. So to turn this off, y equals 2t. At t equals 4, we need to subtract the function and multiply by the Heaviside function at t minus 4. Now, the reason that turns that off is because the Heaviside function at t minus 4 looks like this. It's 0 until we get to 4, and then at 4, it jumps up to 1. That's what that function looks like. So on the interval from 0 to 4, it's 0. So this would be 2t minus 2t times 0, or just 2t. But then on the interval from 4 to infinity, this Heaviside function is 1. So it would be 2t minus 2t times 1. Since we're subtracting it, the 2t minus the 2t gives us 0. So it's effectively turning off that y equals 2t function at t equals 4. Now at t equals 4, we also want to turn this function on. So we will add that function and multiply by the Heaviside function at t minus 4. And you can check if we're on the interval from 0 to 4, the Heaviside function is 0. So this is 2t minus something times 0 plus something times 0. So it's just going to be 2t on that first interval. And then from 4 to infinity, the Heaviside function is 1. So this is 2t minus 2t plus 5t minus 4, because this is 1 and this is 1. The 2t minus 2t, those reduce, and you're just left with the 5t minus 4. So we have our Heaviside function, or excuse me, our function f in terms of the Heaviside function. But I've got some like terms here. I've got a Heaviside function here and a Heaviside function here. So I can add those polynomials out front to condense my f. So that's 2t plus this, 5t minus 4 minus 2t. 5t minus 2t is going to give me 3t. So I have 3t minus 4 times the Heaviside function at t minus 4. So that's my simplified version. Now that we've done that, we want to use our shifting theorems to compute the inverse transform, compute the Laplace transform, forward transform, not inverse transform, of this piece. So I would recommend going to your table if you don't have this one memorized. And this particular table uses u of t minus a instead of h of t minus a, u for unit step function, as opposed to h for heaviside function. It's the same thing. So 52 says that if you have f of t minus a times the heaviside function at t minus a, the Laplace transform is e to the negative as times f of s. Now, if the pattern doesn't match exactly, if you don't see t minus a's everywhere, and we don't have t minus 4s everywhere here, you might be tempted to think you've got a t minus 4 there, but you don't. You have a 3t minus 4. So we don't have an expression that's evaluated at t minus 4. So in that case, I would not use 52, although we could, through some algebraic manipulation, we could show what the result would be. Instead, I would use 53. So this says, number 53 says that the Laplace transform of g of t times the heaviside function at t minus a is e to the negative as times the Laplace transform of g of t plus a. So that is what we will use for this piece. Now that piece is one of our formulas that we've used many times before. We've got a constant times t to some power. You can always pull the constant out because the Laplace transformation is a linear operator. The Laplace transform of t to the n is n factorial over s to the n plus 1. So I'll do this piece and then this piece separately. This piece, I will use this. So for this first piece, I've got a t to the first, so n is equal to 1. So now when I am computing the Laplace transform of f, I just take the Laplace transformation of each piece term by term, bring the 2 down, and this is t to the first, so n is equal to 1, and I'll use this. So the Laplace transform of t to the first is 1 factorial over s to the 1 plus 1, or s squared. Now here, I'm pattern matching to this. So this is my g of t, and this is my h of t minus a. So I think what I'll do is I'll just write that down for right now. Identifying g and identifying h of t minus a. And then we'll go through the process of evaluating this Laplace transform. We're just going to use this. Now, in order to use this, the first thing I typically do is I identify a. Just through pattern matching. If if we've got an h of t minus 4 here, and that's h of t minus a, then a must be 4. And then once you have that, well, we want to identify a and g of t. We've already identified g of t. It's g of t is 3t minus 4. Then I will just substitute that a into the left-hand side here, the left-hand side of this identity for this piece. And I'll simplify this other piece. So I've got 2 over s squared there. And then over here, I'll have e to the negative as where a equals 4. So it's e to the negative 4s. And then I'll multiply by the Laplace transform of g of t plus a. So g of, in this case, a is 4, t plus 4. So we identified a and g. We substituted into the left-hand side, or excuse me, the right-hand side of our identity from our table, entry number 53. And then we just need to evaluate g of t plus 4, or compute g of t plus 4. And then once we do that, we can compute the Laplace transform of g of t plus 4. Easy breezy. So this tells us all the things that we need to do. We need to identify A, find G, evaluate g of t plus A, and then take its transform. So we have g of t right here. And so I'm just going to replace the t with a t plus 4. Now g of t is 3 times t minus 4. So if I give it some input, I'm going to take that input, I'm going to multiply it by 3, and then I'll subtract 4. But now, rather than substituting a t, I want to substitute in a t plus 4. So we'll distribute the 3. We'll have 3t there. Plus 12 minus 4 is going to be plus 8. So g of t plus 4 is 3t plus 8. That will go right there. So the Laplace transform of f of t is this 2 over s squared plus e to the negative 4s times the Laplace transform of g of t plus 4. And g of t plus 4 happens to be 3t plus 8. Now we are going to use the t to the n rule again, and for the 8, we'll use the fact that the Laplace transform of 1 is 1 over s. And since the Laplace transform is a linear operator, the Laplace transform of 8 would just be 8 over s. So we will apply those rules now. Bring the 3 down. There's an implied 1 here. So we'll have, according to this rule, 1 factorial over s to the 1 plus 1, so that's s squared, plus 8 times the Laplace transform of 1, which is 1 over s. And I would simplify. And we have this. For our f of s. That's the Laplace transform of f of t, where f of t was that piecewise function that we started with at the very beginning. So after finding our g of t plus 4, we computed its Laplace transform, and then we simplified. All right, now problem number 6 is next. Here we're asked to use the shifting theorems, the Heaviside function, and the definition of convolution, and the table of Laplace transforms to compute the following. So we have a t times an exponential, e to the t, times cosine of 4t. Now we have a couple of theorems that might apply here. You've got e to the t times a function of t, and we've got a shifting theorem for that, e to the at times f of t. We also have the derivatives of Laplace transforms theorem that says that if this is t to the nth times f of t, there is a corresponding derivative. It's going to be negative 1 to the n times the nth derivative of f of s with respect to s. Like, that's another way to evaluate this if this isn't in our table. And since it's got a product of 3 expressions, the exponential, the polynomial, and the cosine function, chances are it's not in our table. I think the easiest theorem to use is the one where you have the e to the at times f of t, but let's look at our table and show that that's true. Okay, so here's our table. And when we first learned our shifting theorems or translation theorems, same thing. We said if we take a function and we multiply it by e to the at, we end up with f of s minus a. And I thought that was on this first page, but it may not be. Maybe it's at the beginning of our second page. All right, it's number 50. That's what I would recommend that we use here. And that other one that I mentioned was the t to the n times f of t. That's number 55. I'd prefer not to have to take that derivative. I think that 50 is simpler, but in order to do that, we need to identify f of t and make sure that we actually have a Laplace transform in our table for f of t. So let's think of this as f of t times e to the at. According to entry number 50 in our table, the Laplace transform of e to the at times f of t is f of s minus a. So the way I tend to think of it is I take the Laplace transform of f, that's going to give me f of s, and then I replace the s with s minus a. And it's typically notated that way. So in order to do that, I need to identify f of t. That's everything that's not the e to the at. So it's the t times the cosine of 4t. And I want to replace that s after I do that with s minus a. So I need to identify a. If e to the t is e to the at, then clearly a is equal to 1 because the coefficient of t is 1. So we're replacing s with s minus 1. Okay, now I just need to make sure I have an entry in my table like this. So before we do that, let's write down what we just did. First, we identified f. And we identified a. Then we substituted into this first expression here. Okay, and now I just need to compute the Laplace transform of f, which is f of s, and then replace the s with s minus a. And that's easy enough if there's an entry like that in our table. So let's look at our table and see what we have. So if we go to our table, we see that entry number 23 is consistent with this. We have t times cosine of kt, and this is t times cosine of 4t, so k is equal to 4. Now, according to this rule, let's see. Oops, that's not what I wanted. I was trying to annotate. There we go. Here's my Laplace transform of t times cosine of kt. So it's s squared minus k squared. In our case, k is 4, so this is going to be s squared minus 4 squared, or s squared minus 16, divided by s squared plus k squared, so that's 16 again, quantity squared. So I'm just applying that rule. And then I'll just replace all my s's with s minus 1s. So I've got s minus 1 squared minus 16 over the quantity s minus 1 squared plus 16 quantity squared. And that's the answer for part A. So we computed the Laplace transform, and then we replaced the s with s minus a. In this case, s minus 1. Now you could simplify that, but I do not recommend simplifying it, because if it looks like this, it would match an entry in the table, and that would make it easier to take let's say an inverse transform later, something like that. So having those s minus a's quantity squared everywhere is actually going to simplify our work in the long run. So let's look at part B. Okay, so part B asks us to compute the Laplace transform of this integral expression. So it says the integral from 0 to t of tau times sine of tau with respect to tau. So as soon as I see an integral, I'm thinking of the convolution. So we have to match this pattern to the convolution pattern. And remember what the convolution of f with g is. That's the integral from 0 to t of f of tau times g of t minus tau d tau. And so I'm looking for an f of tau and a g of t minus tau. Now I've got this tau expression here. This is a function of tau. So I could call that my f of tau, but I don't see a g of t minus tau. So I am going to multiply by a 1 there and say that that must be my g of t minus tau. So this is a Laplace transform of a convolution of the convolution of one function with another function. We know that f of tau is tau times sine of tau, and g of t minus tau is just a 1. So that means that this is the convolution of f of t. We just replace all the taus with t's. That's t times sine of t with whatever g of t would have to be if g of t minus tau is 1. Now, if g of t minus tau is 1, that means it's a constant function. That means y is equal to 1, or g of t or tau minus t is 1 all the time. So if I go from t minus tau to just a t, I'm just shifting tau units in one direction or another, right? And by shifting tau units, like this would shift g of t tau units to the right. To go from here to here, I'd have to shift g of t minus tau units to the left. Those details don't matter. It's a constant function. If this is equal to 1, then g of t has to equal 1 as well. So the first thing that we did was we looked at this and we identified it as a convolution, or we recognize the integral as a convolution. And then we identified f of t and g of t by pattern matching, by saying the function of tau alone, that's going to be our f. The function of t minus tau, that has to be our g. And since there isn't a t minus tau or an expression evaluated at t minus tau up there, it's just a constant function, it's 1. And if that's 1, then that's going to be a 1. Okay, so now we've got f and g, and now we can apply our convolution theorem over here. Now remember what the convolution theorem says. It says that if you have the Laplace transform of a convolution, you just take the Laplace transform of the first piece and the Laplace transform of the second piece. So that's what we're doing here. This is the Laplace transform of t times sine of t multiplied by the Laplace transform of 1. So I would look for the t times sine of t in my table. And of course, we know the Laplace transform of 1 is 1 over s. And we would just write those down and multiply them together. So I've got a t times sine of t here. Entry number 22 looks like that. It's t times sine of kt. The number in front of your t is your k, so k is equal to 1. So according to that rule, the Laplace transform of sine, or t times sine of kt, is right here. It's 2 times k times s over s squared plus k squared quantity squared. So if our k is 1, this is 2 times 1 times s over s squared plus 1 squared, which is 1, quantity squared. So that's this piece, and then we multiply by the Laplace transform of 1, which is 1 over s. And the s's will reduce when we simplify, and we get 2 over s squared plus 1 quantity squared. So this was our answer for part A. And then this is our answer for part B. Now let's look at part C. Now for part C, we're actually asked to compute an inverse Laplace transform. And we've got a function of s times e to the negative as and a function of s times e to the negative as, where a is 1 here and a is 2 there. So we're going to use this fact from our table. We have the inverse transform of e to the negative as times f of s. And that turns out to be f of t minus a times h of t minus a. Let me show you in our table. Now we've used this before. We just used it in the forward direction rather than the backwards direction. So 52 and 53 involve a function of t multiplied by a heaviside function. And we said that the result of that Laplace transformation is e to the negative as times f of s. So we're going to use 52. We're going to use it backwards. The inverse transform of this guy is equal to that guy. The way I like to think of it is I like to think of it this way. We take the inverse transform of f of s. That's going to give us f of t. Then we're going to replace the t with t minus a. And then we'll multiply by the heaviside function at t minus a. We're going to do that twice because we've got a different a value here than we have here. It's pretty straightforward, actually. So with pattern matching, for this first piece, this is our f of s, and this is our e to the negative as. The product is just reversed, which is fine because multiplication is commutative in the real number system. We can multiply in any order we want, right? So matching that pattern, we see that a equals 1. Now, if a equals 1, what we'll have here is the inverse transform of f of s. And there's my f of s. Now, I don't have a rule as this stands, but if I split this up, I've got one term in the denominator. I've got s over s squared there and 1 over s squared here. If that's my f of s, that will simplify to this. We'll have a 1 over s plus 1 over s squared. That's my f of s. And I'll replace all the t's with t minus a, where a is equal to 1 for the first one. That's just for the first piece. And then we'll multiply that result by the heaviside function at t minus 1. We're going to do the same thing for this piece. This is a different f. I'll just put a little asterisk on it to indicate that it's different. The a is also different. For the second one, e to the as is e to the negative 2s. So a with a little asterisk is equal to 2. So for this piece, we'll have the inverse transform of 1 over s minus 1. And we'll replace the t with t minus a, which is 2, and we'll multiply that by the heaviside function at t minus 2. So that's the plan. We just need to compute this inverse transform and make that replacement, and compute this inverse transform and make that replacement, and then we'll be done. Easy breezy. Now, the inverse transform of this piece is just 1 for the 1 over s, and 1 over s squared would come from taking the inverse transform of something that looks like this. Get a t to the n. So if n plus 1 is 2, then n is equal to 1. So this is 1 factorial over s to the 1 plus 1. So this this inverse transform is t to the first. And we're going to take our t's and we'll replace them with t minus 1, and then we'll multiply that result by the heaviside function at t minus 1. Over here, we take the inverse transform of this piece. That's e to the inverse transform of 1 over s minus a is e to the at. So that's e to the 1t, but we'll replace the t with t minus 2, and we'll multiply by the heaviside function at t minus 2. So I have 1 plus t minus 1 times the heaviside function at t minus 1 plus e to the t minus 2 times the heaviside function at t minus 2. Of course, 1 plus t minus 1, the 1 and the negative 1 reduce, and we just get a t. So that is the inverse transform that we were looking for. But I would recommend writing it as a piecewise function. Anytime I have a result involving a heaviside function, I always want to get it back into the form of a piecewise function. So if this is my f of t, let's call it f of t to give it a label. It's going to have 3 pieces because I have a heaviside function at t minus 1 and one at t minus 2. So we'll have a certain value on the interval from 0 to 1, and then we'll have a different function on the interval from 1 to 2, and then we'll have a different function on the interval from 2 to infinity. And usually we put the less than or equal to signs on this side. Okay. On the interval from 0 to 1, so remember how these Heaviside functions work. The Heaviside function at t minus 1 is 0 until we get to 1, and then at 1, it's equal to 1. And the Heaviside function at t minus 2 is equal to 0 until we get to 2, and then it's equal to 1. Okay, so on the interval from 0 to 1, both of these are 0. So this is t times 0 plus this exponential times 0, so we just get 0. Not much going on the interval from 0 to 1. On the interval from 1 to 2, this Heaviside function is 1, but this Heaviside function is 0. So we'll have t times 1 plus the exponential times 0. So it's just going to be t on that interval. And then on the interval from 2 to infinity, this Heaviside function is 1, and so is this one. So this is t times 1 plus the exponential times 1. So we just get t plus the exponential. And that would be our answer. Now, if you're in my class and you said, Miss Townsend, I didn't do that, I just stopped there, that's totally fine. But it is good practice to write these functions in this way because people are more comfortable with the piecewise representation rather than the Heaviside function representation. And this also shows me that you really understand what the Heaviside functions mean and that you're not just sort of memorizing patterns without remembering like what these functions actually do and what they are. Let's see, how did we do that? We identified f, we identified a, we took the inverse transform of f of s to get f of t. We replaced the t with t minus 1, and we simplified. Here we identified f, we identified a, we took the inverse transform of f of s to get f of t. We replaced the t with t minus 2 and multiplied by the Heaviside function at t minus 2. And so that is how we ended up there. So that is the end of our problems for quiz number 6 for version number 2. And these are the problems covering standard L26, which is about the shifting theorems or translation theorems, the unit step function, and the convolution. And this is a standard where you would just be asked to compute the Laplace transform or the inverse Laplace transform using what you know about those functions. In another standard, those functions may appear in the context of a differential equation, initial value problem with a derivative or a differential equation in it, or an initial value problem featuring an integral differential equation or an integral equation.